Hello, Math 4 students. Mr. Van here. I um, I wasted a little time today, although I don't know if I would call this a waste. Um, Honestly, no idea when I'm going to use this, but there's lots of cool math stuff going on here, and I don't know. We might talk about this in class at some point. But the topic for today is section 1.5, which is not that stuff. It is this stuff: parent functions and transformations. So what we're going to be doing is we're going to be looking at a few function families. We're going to talk about the parent functions, and then we're going to talk about just functions sort of in general and things that we can do to every single function to change them in a variety of ways. We're going to be able to shift them left and right. We're going to be able to move them up and down. We're going to be able to stretch them out, make them skinnier. We're going to make them squish them and make them wider. We're going to be able to do all kinds of stuff. We're going to do some reflections too. So let's just sort of take a look at a few of these parent functions. We have a constant function, which is just a horizontal line. We have an identity function, which that's just y equals x essentially. We've got the quadratic function, f of x equals x squared. And a cubic, you've got a square root, and the reciprocal function, 1 over x, and your absolute value, and your greatest integer. So those are all the different functions that we're going to be playing around with. We're going to be modifying, changing, altering so that they look slightly different. So the first thing that this really talks about is just describing characteristics of a parent function. So you've got domain, you've got range, you've got x-intercepts, y-intercepts, there's symmetry, there's end behavior. These are all things that we should be able to talk about and apply to any function. The nice thing is, if a parent function has a particular type of domain, then every function in that family has basically the same type of domain. The domains aren't going to be exactly the same, but you'll see what I mean in a couple minutes here. So let's take a look. We did a Desmos activity last week dealing with transformations, so you should be pretty familiar with vertical and horizontal translations. A vertical translation can be accomplished just by adding something to the end or subtracting something to the end. If you add something, you move your entire graph up. If you subtract something, you move your entire graph down. Horizontal translations are a little bit different. They're a little bit weird in that they kind of go backwards of what you would expect them to do. I haven't really been able to come up with like a great way of explaining this, but the way I've been able to explain this, which seems to sort of make sense to people, is that when we subtract something from x right away, what we're doing is we are delaying our function, making it seem like it's coming later than it normally would as we read our graph from left to right. So if we have f of x minus 2 for this particular function, what's going to happen is normally we would expect to see the lowest point here at the origin, but as we're reading from left to right, we're going to find that point 2 spaces later. Now, just like this delays our function, adding to x will actually move our function up. So as we're reading from left to right, we encounter this point sooner than we normally would have because we're adding to the x values. I hope that makes sense. That's really the best way I've been able to explain it. I don't know. There might be a better way. I just don't know it. All right. Absolute value of x. They're just showing you a few different examples of how this works. Add a 4 to the end, the whole thing moves up 4. You add 3 inside, you're moving the whole thing left 3. You subtract 2 inside, that's 2 to the right. And you subtract 1 on the outside, that's down. So you go right 2, down 1, and you have the exact same graph. The shape has not changed at all. So this one right here, if I would just quick sketch it, it's my cubic function, but it's shifted down 5. So it would, 1, 2, 3, 4, 5. So it would look something like something better than that. But that's, you get it. This one right here, x minus 3, that's going to shift it to the right 3, so it's going to go like that. Plus 2, that would move it 2 to the left. Plus 4, that would move it up 4. So instead of having this curve, it's going to go like that, basically. And that point right there is 2, 4. Thought I was going to sneeze. It didn't work. Moving on. Reflections. So you can get a reflection of your function across the x-axis just by putting a negative out in front of your whole function. And effectively that just flips it over here. And you can flip across the y-axis by putting a negative in front of your x over here. So instead of this, it gets reflected over here and goes this way instead. So if we take a look at this, it's flipped over, moved 1 to the right, and up 2. So normally it looks like this. And then you flip it, and then you move it 1 to the right, and then you move it up 2. And that's where you end up. What I would suggest that is, as you're first kind of starting to get used to these, type them into Desmos sort of like one little thing at a time. Like start with the parent function root x, and then start adding to it, and you can see how each piece will change your function and move it to where it ends up. Writing equations for transformations. Well, if we take a look at this thing, normally it would be over here, but it's been shifted over by like 2.5-ish, or well, this says 5. I don't know why that's 5. That doesn't look like a 5 to me. 1, 2.5. That's weird. Whatever. They just got odd scaling, apparently. Yeah, blah, 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 so on and so forth. Let me see here. Reflections, vertical and horizontal translations. Dilations. Okay. I'm sorry. I know this is gross, but I gotta blow my nose. Too deep into this video to start over again. Alright. Allergies, man. Alright, so vertical dilations and horizontal dilations. Dilations are just what we refer to as a stretch or a squish, or a stretch or a compression, if you want to be more technical about it. I like to think in terms of a squish, though, because I guess it's more fun to say. I don't really have a good reason for it. Anyway, now, just like when we modified the x before, when we added to the x, we actually moved left, and when we subtracted from x, we moved to the right, which is the opposite of what we would expect. It's going to be the same thing whenever we do some sort of multiplier. So if I put a out in front here, as long as a is greater than 1, or the absolute value of a is greater than 1, I end up with a skinnier parabola. If it's somewhere between 0 and 1, or at least the absolute value, I don't know why they get this wrong, it squishes it, and it ends up being wider. Now, it's the exact opposite when you've got a number inside the parentheses. Generally speaking. But, that is not at all what I would have expected. Weird. Moving on. We'll come back to that if we need to. Oh, yeah, so both of these are flipped and squished and blah, blah, blah. Piecewise functions. Okay, so with piecewise functions, these can be a little bit tricky to graph, but you can graph it on Desmos. I'm pretty sure I showed you how to do it, where you put in the piece of the function, and then in the squiggly brackets, you put exactly what we've got written here. You just put x is less than -1, and it'll cut it off at -1. You can also draw them by hand, but that's a little bit harder, and I don't know. I'm not a big fan of drawing graphs by hand these days. It's good to be able to sketch them, but to like get a really accurate graph, it's a waste of time, generally speaking. So transformations of functions. If we take a look at this thing, we can rewrite this quadratic that's in what we call standard form into what we call vertex form. And vertex form is helpful because it shows us all the translations, all the transformations from our base function of just x squared. So just looking at this thing, I know it's shifted to the right 30, up 61. The negative makes it flipped, and the 1/15th will, well, okay, so we went right 30, up 61, negative flips it, and then the 1/15th will squish it so that it's much, much wider. Yeah. So the way that we get it into that vertex form is by completing the square. And yeah, if you have questions about that, let me know. We'll talk about it. So moving along, moving along. Oh, you can do some weird stuff with absolute values, like some really weird stuff. Basically, whenever you do an absolute value of some sort of function, it's going to cut off anything that's in the negative zone and reflect it across the x-axis. So normally this would come down like this, but this bottom part here has gotten cut off and flipped up, so then you get this like bounce in the middle. Over here, when you put the absolute value inside the parentheses, what it does is it cuts it off at the x-axis and takes whatever's on the right side and reflects it over onto the left. So that's why you have this weird looking bounce there as well. This one has both, it looks like. Yeah. Weird. And that's about it. If you have any questions, try it out on Desmos or send me a message. Bye.